Good afternoon, everybody. Thank you all for staying so long. And as we've been hearing, I hope this will be the last and the best presentation too. And also, I leave the second half of the presentation to be even more interesting because this guy, my boss up here, he's a cool guy, and he'll show off some real nice code. So I'll do some of the boring talk to start off. So what we are part of is Genesys, and within Genesys we are the applied research group, and this is a new group that we have formed, and we are starting to look at analytics of text as something that we will be exploring more and more. And this is some of the initial exploration in that area. And what is Genesys? Genesys is a communication software company, and we're geared and we help our customers drive their customers' experiences. And within that, our group in the past has been primarily focused on media processing, all kinds of media, and now we are more into the research game. So, some of the things that I'll cover today is more related to text. You've heard a lot about neural networks, and obviously neural network will be a theme in our talk as well. So I'm going to bring in the concept of what's called word-to-vec. It's a novel approach where you can represent words as a vector in a semantic space. And then I'm going to talk a little bit about an application that we built, and Felix will show it off after the time. All right, so what is text analytics? There are buzzwords around and people talk about it. So what is text analytics? In a nutshell, it's basically trying to get meaning out of unstructured data. And in our case, it's text. So you can have text from a Twitter feed. It could be a review on an online shopping website, what have you. So what can we get as an information from that? And it's completely unstructured. So you would have a sequence of words, a sequence of characters, and how do you make sense out of it is the main goal. So it commonly shows up in many of these applications. Some of the common things that you use on a daily basis is for search engines. So you want to retrieve some information, or you're interacting with a machine or a bot. So you go and ask a question, and the bot is supposed to go look up all its resources, figure out what the best answer is, and then respond to you. It's also used in kind of context-aware advertising. We had a talk about that, a lightning talk a little bit. And then spam detection. Just by looking at the content of an email, can we figure out whether it's spam or not? Sentiment analysis is where, if you have reviews, can you figure out what is the sentiment within that review? Some people might give you a mediocre rating, like they might put 3 stars, but their sentiment when in the actual verbatim text could be a little different. And customer care is another field where you can analyze Twitter feeds. If your company is getting bad Twitter posts, then you would want to know that. And what is an automated way? You could use text analytics to do something like that. So then this is a question that's probably answered, but I'd like to phrase it in a short manner. What is a neural network? A neural network is a biologically inspired model which learns from data. So having said that, I look at neural networks as one of these two. It creates one of these two functions basically. It acts as a function approximator. So you have some input and some output. Can we build a relationship between the two? It can be as abstract and as complex as you want the relationship, but the neural network helps us to do. This is not the only way to do, but this has been an efficient way to do. And another one is a probability estimator. So you have a classification problem. You need to know whether it belongs to a cat class or a dog class, as examples we have seen. So it estimates a probability. Another thing that I'd like to point out in a neural network is it's basically fundamental operations. It has primitive operations of addition, multiplication, a dot product, and a nonlinearity, and that's about it. So you build a really complex function out of these primitive operations. So it can model well because these primitive operations occur in many places, and you can scale it up very well. And nonlinearity is another important feature of the neural network's primitive operation, which helps it to learn really complex tasks. So I want to contrast how the neural network can be actually represented as a simpler model. So let's take a simple linear regression model. We just saw in the previous talk what a linear regression task can do. So if you have a line type relationship, x equals mx plus c, y equal to mx plus c, you can represent it with a line in 2 dimensions. And in a higher dimension, it's basically a summation of weights to your input, which gives you the relationship to the output. So this is a simple linear regression model, and this has served very well for decades in the past. So now, if you have categorical data, or if you want to do classification, linear regression doesn't do as well because one of the first things that happens is you can, and if you have 2 classes, say let's say 0 and 1, and if you try to fit it with a line, you would end up getting negative values, which is clearly not a class label. So you have to do some thresholding on top of it and stuff like that. So then came logistic regressions. So this is basically a very similar model to a linear regression, but you throw in a nonlinearity in front of it, and that's the sigmoid in this case. And now you are able to predict probabilities. So in the curve on the right, bottom right shows you have 2 classes, and you fit a sigmoid curve. And the output of the sigmoid curve gives the probability. So now, if you scale this up, you just look at the piece at the bottom and look at this big network, which we've seen quite a few times today. It's basically the same thing repeated. So a neural network at the end of the day is just the same operation as a linear regression with some nonlinearity. And at the same time, there is a hierarchical structure. You have layers of these operations fed from one layer to another, so the information flow is hierarchical. So I think we saw in another talk this morning that the first few layers tend to do the feature engineering, and then eventually the object representations in the later stage, which is a very accurate way to represent that. And finally, we've also heard this buzzword of what is deep learning, and many people use deep learning and deep neural networks as interchangeable words, but in reality, deep learning is the methodology to learn the networks, and there is a class of methods that have been come up in the recent past, which has enabled us to learn really complex and big networks. And second, the deep neural network term is also not very well defined. People just say if it's a large number of layers. There's no fixed number. So the larger the number of layers, you can just effectively just call it a deep network. So I'll talk a little bit about the types. You've seen a few in the recent talks, and the simplest is a fully connected dense model. So every input is connected to the output of a layer, and this is a very popular one, and actually is probably will serve the it'll serve very far. Actually, it does a pretty well job in most examples. But if your inputs are really large, let's say the image example that was given, like if you have 786 dimensions, or if you want to operate on even larger, larger images or larger frames, the scaling of a feed-forward network becomes more of a problematic issue. So then you start introducing what's called the convolutional neural network. And I'd like to present this in a different way. And this is basically a feed-forward network, but I'll show you in another slide in the future that it's basically your parameters are shared and the connections are not fully connected. And the feature engineering is also done by such layers because these capture the edges or the textures or what have you from an image. And then we've also heard the recurrent part, where memory is important if you're doing your operation on a time series or anything that needs memory. And finally, there are more complex networks like the LSTM, which was also brought up in the morning's talk. This is built on top of a neural network, a recurrent neural network, to avoid some of the problems in RNNs. So I'd like to talk a little bit about convolutional neural nets because that's what we've used and that's what we'll be talking about. So it scales to very large inputs. That's one of the key important factors that most people use it for. It does feature engineering also. So the sparsity of the connection is the main thing. Let me put up a graphic here. So basically, a convolution operation is a dot product. In a fully connected network, you take the parameters from your input and you do a dot product with the weights of that layer. But in this case, you would have a smaller kernel. So as a representative example here, I just have a kernel of size 2. You take it and you slide it over your input. Here, my A through G is the input. And this is the second one is the layers, that layer's output. So as you can see, the connections are very sparse. A is not related with G at all in any way. So this brings in the localness, or it uses just the locality of the image, or in our case, it's a one-dimensional thing. And I've represented it as a one-dimensional thing because this is a sequence of words. That's what we would be analyzing in the future. And the convolution of a two-dimensional kernel can be represented as a bigram, which is a common term used in natural language. And the 3 kernel is a trigram, and a 4 is a quadgram. So you're stitching 3 words together and calling that as an entity. And that gives us boosted results, because as you add more context to words, that's when you add more meaning to those words as well. Excuse me. A quick talk about word2vec. This is a topic that can actually be a talk by itself. A common way to represent a word. So we've seen neural networks to be accepting numerical data. And when we talk about words, how do you present words to a neural network? One good way would be, if you have a vocabulary, if you have a fixed vocabulary, you create a big long vector of zeros, and whenever you see a word in, say, index number 3, you just set it to be 1, saying that that word was found, or that's the vector representation of that word. So clearly, this kind of a representation has its own problems. One is it's so sparse, it'll make your dimensions so large. In a typical English, there is actually the upper bound of vocabulary is not known. But there are systems which are built with vocabularies in the millions, so which takes into emojis and all kinds of stuff. So it really gets into the millions. And then the second thing is it's actually very sparse. The information in that vector is very low. It's just one value. And then there is another third problem. Can anybody see what would be what would be a main problem by using such a representation? Let's say you have one word like this, and another word has a whole bunch of zeros, and just one value is highlighted as 1. You lose context. So when you mean by that, yeah, please. Yeah. So if you want to look at the difference between 2 words, it's always the same. You take any 2 words, they are almost the same. They're off by the same distance. So it's pretty much useless as semantic. It doesn't have any semantic representation. So word2vec comes into picture where it can capture the semantic representation. Or in some sense, I don't know if the actual researchers went out to find the embedding to be in that fashion, but it turns out that it captures the semantic relationship very well. So what is word2vec? On the right-hand side is what you see, a network, just a 2-layer network. So the input to that is that big, long, one hot encoded vector. And on the right is all the neighbors of the vector of that particular word in that context. So, if there's a typical word like, I love IndyPy, then love is in the first word, I love IndyPy. So you're predicting the neighbors of a given word. So if you train this over a really large corpus, you start seeing the dimensionality reduction in the central hidden layer. I would like to mention that the hidden layer has a much smaller number of nodes, and that's typically in the order of hundreds. Google has a word2vec which is readily available for anybody to use. They have trained it on billions of tokens, and that is of an order of dimension 300. And to illustrate how there are semantic relationship between words is contained in this word2vec, you can have semantic relationship you can actually do arithmetic on it. So basically, you can take the vector of the word king, subtract the vector of man, which should be approximately equal to queen minus woman. So the common denominator between the two is royalty or something in that sense. So this, now you can actually add words, multiply words. You can do a whole bunch of things because you've just formed it into a vector space. People have attempted to do this with images as well. So you can take an image of a human being with glasses and say minus glasses, and you get a picture of the human being without the glasses. So it's pretty fascinating. So I'm rushing through because I would like to spend more time on the code. So we've seen a whole bunch of data processing in the previous talk. When you're specifically looking at text data, these are some of the pre-processing tasks that we would do. First thing is, you're given a sentence. You need to tokenize it into words. It appears to be a trivial task. Oh, I'll just use dot split in Python, but in some of the other languages, it's not trivial. Like take example Mandarin. You don't even have spaces. How would you go and split it? So it needs more systematic approach for doing tokenization in other languages. And then stemming and lemmatization are similar in how they are used or what their effect is. So you have, let's say, plurals. In this example, ponies. And you want ponies and pony to mean the same in your processing. So I'm looking up pony, and if I'm doing a search for pony or ponies, it should give me the same results. So stemming is one way to do it, but it does not do the best job all the time. But lemmatization actually goes and finds the singular form of it. And then finally, there's the stop word removal, and stop words are basically not information, words which don't contain information, things like the, is, I, and stuff like that. We just remove them. And so this is an application we built, and I'd like to just share what the overall architecture is. So the input, let's say, so this is an interaction steering application. What I mean by that is, somebody will be talking to a bot. So they'll come and say, hey, please cancel my subscription. And we need to figure out which bucket to put that interaction to so somebody can help the individual properly. So somebody's coming in with a query. We need to figure out which agent will be best able to help it. So in this case, we have 5 agents as an example here. If there was a question about billing, it goes to the billing agent. If it's a question about cancellation, it goes to cancellation, and so on and so forth. So the way we do this is each of these words, which are tokenized, we get the embeddings, and that's what this box represents. And each of these embeddings are passed into 3 towers of convolutional neural nets, one representing the 2 grams, the trigram, and the the quadgram. And then further in the depth-wise dimension, we have multiple layers, multiple filters. And those filters capture different features. So one of them could capture the relationship between 2 words. The other one could capture, what have you. This is the part where neural networks don't give us what they capture. And then these are activated with ReLU activation functions. And then max pooling is an operation commonly done on images just to reduce the number of nodes that we have to handle. And it also works as dimensionality reduction, roughly. And then we merge and just use 2 dense layers to do the actual classification. So the first convolution part is doing the feature engineering, and the second part is doing the classification. So with that, I'll pass it to Felix. Yeah, please. Yeah, sure. This is time for questions.
Are you using different data sets to feed the models depending on, say, like different customers? Like you got a customer who does HVAC and you got a customer who does tech support for PCs. They're going to have very different vocabularies. Do you feed different data sets in this case, or are you using a generic model for everybody?
We could start with a generic model. That's what we usually have done. And the data set we have is actually specific to a customer, Microsoft in this case. And the queries are specific to Microsoft. You would definitely do very well if it's specific to that domain. But you can start off with a generic model to begin with, collect data, and then improve on top of it. Oh, yeah, sure. Well, keep in mind, these filters are not what we describe. The training picks those filters. So that's why the feature learning is done automatically. We don't tell what is the features. We just say, hey, give me, in our case, 32 filters. So the filters are automatically learned. Sure. Yeah. Yeah, it's trained, actually. So all you give is the dimensions and the number of filters. So you randomly initialize it, and then the training actually learns the filters. So it determines which attributes are important for the classification task. So if you were doing some other task, the filters could look completely different. Yeah. Okay.
Can you elaborate a little bit more on how you reduce from like 3 million number of words to, in this context, is it like 6 words that is our bank? So, for example, please would be one of the 6 columns, and that row would be 1, and the other 5 would be 0. How did we decide to have 6? So this is an example. But how many? How did we reduce from 3 million words to a smaller sample?
That's the embedding, exactly. Sure.
At this point, it would be like an image. This would be treated like an image in our CNN, right? An image that has a bunch of zeros and then ones, 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 and it's essentially like an image of ones and zeros. It would be treated like that.
No, 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 not necessarily. The rows in this matrix are the outputs of the embeddings, and actually Felix will show out an image of the embeddings. So those are not 0 and 1s. Those are actually the output from the hidden layer. So the first layer is, so you don't actually have to create that million length vector. You don't have to do it at all, because this is done in one shot, and even if you want, you can use the Google's model, so you don't even have to do the training of the embedding.
So those 6 are actually 300 that you
Exactly. Yes, yes, exactly.
Okay, so you did not design this. You used the Google.
No, we did, and as I said, Felix will actually show the embeddings too, so he'll plot it in a, no. Yeah, sounds good. Yeah. I, how did I come up with the network architecture? So this is kind of, this is mostly the traditional way. Like if you've seen ImageNet, they do similar things. They have a bunch of convolution layers in the beginning, and then they have feed forward. We kind of followed that theme. Most likely, we can simplify this a little bit because our task is not overly complicated. So again, this is the same question. It's hard to come up with a well-defined network. So you start somewhere and then try to refine or simplify. All right, cool. I'll pass it on for the nice part.
Okay, welcome. So let's show some code. I think you guys would like to see some Python, I think, and also with respect to the architecture, I think Ananth alluded to that. Really, the idea of those convolutional towers is that they represent bigrams or like combinations of adjacent words. So bigrams, trigrams, fourgrams. Anyway, so I think I need to exit the presentation here. What happened? Okay. Is this large enough? Can everybody see this? Okay. So make sure it all starts fresh. So I'm actually doing this, running it live. So I'm a bit of a risk here. But so one of the things we do first, which actually I ran into, was relatively difficult. I think Lisa alluded to the fact that you want to randomly seed, but it's actually nowhere nearly as simple as it looks, because in particular TensorFlow is very picky, So at first it looks like you have seeded it, but it really subtle differences sneak in. So I finally, with some Googling and some tests and some playing around, found a way to really initialize it so that you can reproducible results in a notebook. So this takes a little while.
Can you make that one bigger?
Let me see. I hope, okay. So first, we need some data. Now, as Ananth mentioned, this is basically, this is some data from a real customer we have 5 classes of basically utterances were actually transcribed from people calling into their support line. And we need to identify, we want to classify the input text into one of those 5 classes. And so for each of those, we have about 1,000 sentences. And I can show some of how they look. I said some examples here. So this is basically the input kind of utterances that we expect. Similar, so this was for cancellation. This is for, say, for the security. And so the first thing we now do, we need to tokenize that. We remove stop words, tokenize it. And so we see we have 5 classes here. We have about almost not quite 7,000 of those sentences. Now we want to tokenize them, and the way we do this is we create an index. Actually, that's Keras does that for us here. So create an index. The most frequent word gets value 1, and the least frequent word gets whatever the last 6,823, and simply uses those as a binary or as an integer value that represents that particular word. Because then, if you remember that one hot vector representation that Ananth mentioned, so instead of having a vector that has, in this case, 7,000 cells, with most of them, or all of them 0 except 1, we simply represent this as just a number. So you can see here, there are actually 2,100 distinct words in that corpus here. So as a test here, my mouse doesn't work, so we can see, oh, it actually only 3 of those indices came out. That's obviously because some of them are stop words, which really don't add any semantic value in for this task. So now if we turn it back into words, we can see mouse not work. So now, the input that will feed into this network is obviously this sentences. Now, as we saw here, there are some that are really long and some that are relatively short. And so what we do here is we pad them to the same length and truncate them. And so this is, again, all functions are provided by Keras. So now we can see here, this actually now is a matrix with 15 columns and our 6,800 rows. And so we can see how that looks, and it's actually padded to the right, but that's more that's a default setting, but that can be changed, but that doesn't really change the result. And it's actually configured that it uses the last words as opposed to the first pads from the beginning, as opposed to the end, or truncates from the beginning as opposed to the end, and that can also be changed. Now, as we saw, our topics are basically a number between 0 and 4, but we really have categorical data. We want to have this, the output of the network needs to be, it's either this or that or that or that. It's either billing, cancellation, hardware, or security, and at least with a certain or a probability, how likely is it a particular class. And so there's a nice function to categorical that basically turns this into a matrix with 5 rows, where each class, again, is a one hot vector with zeros and a one where for a particular class. Now, Alyssa again showed how we split this into training and test and training set. And here, I'm actually, because we have relatively little data, I'm just using a relatively small test set, so that obviously that risks overfitting, but there is a trick we later use to avoid this. So here we can see we have about 6,000 training samples and 1,000 test samples. So now we built the model. So first of all, Ananth mentioned the Google word to vec is 300 has a 300 dimension output. Here we really want to do that because this is built from scratch. I'm not using any external corpus or pre-trained model. So we're going to use a very small embedding. Just pick 10 as an example here. So the output of our embedding is only 10 dimensions. And so now we're basically building the model as we saw on Ananth's diagram. So first we do an embedding, which is that mapping. And then we have those 3 convolutional towers. And we can see there are 32 filters here, as an example. So that means actually there is 32 stacked filters. And then we use a global max pooling, which means that at each point, or at this point, it picks which of those convolutional filter outputs for each of those 32 towers has the highest value, and it picks only this one, that particular one. So that would mean for each of those filters, in this one, this could be the most important pair, for example, or whatever trigram or 4-gram, and so then it at each level picks that, and so then our output of the global max pooling is basically for each of those filter lanes, which one has the highest value. Then we concatenate them, and then we have these 2 dense units. Now, one key that we do here is we do a dropout, and relatively aggressive. A dropout is only used during training, and what it means is as we train, at random, we basically not feed the output of the previous dense layer to the next dense layer. So that's like if you take, as you learn, as the network learns, you simply just pick half of the neurons and say, you are not turned on, even though, or I don't care what your value is, I just only train with the other half. And that is very useful for cases where you risk overfitting because you have very low amount of data, and it adds robustness to the trained model. And so then we have the dense output layer with a softmax, and which picks basically which of the outputs has the highest confidence. And so if we build this model, and now in the summary here, we can see, I have to make it a little smaller here. We can see here that, again, we have these convolution layers with 32 lanes each, and after the max pooling, basically we have 1 for each, so 96 inputs left for the next dense layer. And we see overall, this network actually has 31,000 trainable parameters. And so given that the data is relatively small, again, so that there is a considerable risk here of ending up with overfitting if we're not careful. So now we can train this and see. So you can see it actually converges relatively quickly and gives a really good confidence or a really good accuracy, and both on our training and on the validation. Because again, as Elissa mentioned, often if the training accuracy is really high and the validation accuracy is low, that's suspicious. Fortunately, that's not the case here. And again, the dropout helps with that. So we can see basically our accuracy on this task basically it seems almost suspiciously good. So let's run a few tests. So here I have a simple helper function that takes a sentence input, converts it to sequences of words, and then pads it, as we've seen above, and then it feeds it through the model and picks which of the class is highest, and prints the class and the confidence. So my mouse doesn't work, hardware problem. I want to cancel my service, obviously. please stop my subscription. So we see that it's pretty confident. Right. And I want to speak to a human. Well, that's, yeah. It's pretty clear what he wants here. So really the interesting part on this here is really the embedding layer. Let's look at, in particular, what actually happens. So we have this high-dimensional input that's fed into, turns into just 10 values, and then, so what exactly, what happens here? So what I do here is I build a new model that's simply just an embedding layer, and that I don't train it, but instead I set the weights of the trained model into it. And so now if you look here, let's say I take a few words, and here we have the sequence of those indices, and if I run that through that embedding model, we get this, for each of those words, we get a 10-dimensional vector, as you can see here. So now let's see how similar they are. Again, now that's where that king and queen, man, woman kind of comes a little bit into play. Of course, this is specifically this task because you had no king called and no queen, so there's no that won't be in there. So basically, we here do a cosine similarity, something that was mentioned this morning. So yeah, human and representative. So cosine similarity, 1 means it's perfect alignment, -1, it's perfect opposite. So it's kind of again the angle between those vectors. So yeah, that's pretty clear. Mouse and keyboard is, yeah, they're closely related in this task again. Human and mouse, not really. Password and login, yeah, that's obviously a clear related problem. Password and hacker. But now let's look, he's a hacker, a human? No. So here you can see, that's purely because of the data set. So the neural net doesn't know what a hacker or a human is, or that the hacker really I think usually they're human, but generally, again, the neural net doesn't care. Okay, so now, yeah, so this worked well, so let's actually, everybody wants to see some pictures. So what I do here, and it takes a little while, so I have to kind of talk over this. Basically, there's a dimensionality reduction approach called TSNE that allows you to visualize high-dimensional vectors. It's a little bit of a hack trying to just pick the best way to represent it, and it even says kind of, I think Hinton invented it, and he basically says, well, just try some values until it looks good. So it can't be used to as a dimensionality reduction for classification, but it works. It works well. So then what I do is I print a scatter plot where the most frequent word, so the ones based on you can see based on the index, the most frequent word is red, and then it gets cooler as they get less frequent. And so we can see here, the frequent words are clustered clearly into these areas here. And as we saw, there were 4 kind of very distinct classes, namely and then the other, that's kind of, well, any question that was asked that couldn't really be answered has to go through to an operator, a human. Then, so we can kind of see, well, that looks pretty reasonable. So now let's drill down into this a little bit. For example, here, so I have wrote a function that basically can provide a list of words. Okay, it's actually a string. It takes each word, it finds where it is, and shows kind of the surrounding words. So let me run this. For example, credit card, bill payment. Obviously, they should be kind of related, and we can see this here. And so if you look around, it makes sense, right? So dispute, charges, invoice, declined. So this very closely related terms. Similar like a keyboard, mouse, and monitor. Again, it's clearly hardware related, and there are other, right? Device, driver, battery, whatever. So, and again, this is strictly just from this data. There is no other from these few thousand sentences. And here, password, logged and login. Again, it's clear that this is very semantically related. Operator and person. Yeah, and so we can see here, right? Technician, representative, employee, customer, supervisor. So it's, again, it clearly identified where, or kind of the related concepts. Now, I don't know whether that works. Sometimes it doesn't. Can actually do an interactive plot, and I need to be a bit careful because there are actually words in there that are not really really for okay, ladies are present. Yeah, so again, we can drill down. We can see, so actually we can drill down into some other areas here. Yeah, and of course, this actually only shows the 500 most common words. The rest are kind of, otherwise it turns into a black mass. But we can see, so as the further in we go, the less related they are. It's also because there's less information or fewer examples that it saw. But here, see, I mean, there's, yeah. Anyway, so that's kind of showing, drilling down a little bit into code here. You for time. Okay. We have another thing, because this little project actually came about from a hackathon that we did internally, and the system that was built actually had a web front end and also supported speech input. So let me run this here. This actually is a Docker. I'm running here a Docker container that runs a Flask app with an API, and so from the website, and then you can submit. Let me make sure this takes a little while to run. So let me. So this actually has two input. You either can ask the text, but that's pretty much what we show, but we can also do speech input. So it actually has, we can record speech, it's submitted to this Flask app, then it spawns our speech recognition engine trained with a language model that uses those words. And so here, I'm actually using web audio to capture it and then again submit it to the engine. Now, there's a lot of reverb here, so I'm not sure whether this will work. So if I say, my keyboard doesn't work, yeah, I think it's too, although at least it would go, I didn't understand it, but let me try. My keyboard, yeah. Yeah, there's too much reverb in the. My keyboard doesn't work. Yeah, there we go. And so. Anyway, so any questions? Yes, the data is. I can't hand out the data. But you mean the notebook? Yeah. Well, I can give you the notebook. I mean that's but the data I can't give you the data. Okay, yeah, sure. So probably I don't know whether do I just give it to you or do you want to just?
We have an IndyPy GitHub repo, and I'm going to collect the presentations. We'll put them up there.
Okay.
So I noticed you had special stop words.
Mm-hmm.
Could you speak a little bit to like the length, not necessarily the number of records, but the length curious, like, if you had longer words in your documents, essentially, how would that affect your ability to classify it? Does that make sense?
Oh, you mean if the sentences are much longer?
Yes, okay. Like the examples you gave are very short. Does that match with the training data? Could you speak to that a little bit?
Well, I mean, specifically, obviously, to the task here, right? The task is identifying kind of what is it about. Now, obviously, if it's much longer, then if you have multiple concepts, even then once you get to the representative, and then say, well, but I told the system already. So one possibility you can do there is you use this for a pre-classification, and then we can, based on identifying, oh, this is about billing, then we can, for example, look, well, did they say an account number? So then you can start drilling down into the data specifically to that. But of course, that's more a system integration, application level kind of design or architecture then.
So I guess the other way of asking the question is, if you had an input test. So if you had another way to ask this question is, if you had an input test that was much longer than your training, statement, how well would this work out predicting from that?
Well, like I said, in this case, we basically we basically truncate it, and it actually truncates from the right. So it just picks basically the last 15 words that weren't stop words.
Thanks for the presentation. Lots of questions. So how do you settle on CNN versus RNNs or LSTM?
Well, again, because in this case, because it's simply a classification, and we assume that, again, it's mostly concepts, right? Again, so n-grams would be most likely sufficient, and so it keeps it simple, and as it works. Yeah.
And then the next question is, do you have to deal with synonymy listening?
You can. Now, there are two possible ways, right? Either, but here, again, this is because it's really kind of simplified, right? We don't do stemming, we don't do, in this case, there's a stop word removal, so no stemming, but you could, first of all, you could easily expand synonyms, because that basically adds to your training data too. I mean, that's, again, NLTK has support for synonym expansion or WordNet. I mean, that's an easy way to just, and then have it learn those, but you could also then expand during query technically, right? So that would, again, it depends on kind of the test it.
Any other questions? Still got about 10 minutes we can take on this. Yeah.
Okay.
Was this the first architecture you tried? Was this the first architecture you tried?
Yeah, pretty much.
But you just got lucky?
Well, I mean, I think
you explored simpler versions, and it's more.
Yeah, I mean, actually, I tried with, for example, only having two towers. This seemed to have worked the best. Now, again, this was a really kind of very simplified kind of again a very small data set. Now, if you have a much larger data set, then we're probably adding more lanes and also larger filters. But a lot of that kind of is trial and error. I mean, that's generally, I think, again, Alice alluded to it too. I mean, sometimes you have to kind of try and then see what's the smallest one that gives good results. Because in a commercial setting, speed and cost is kind of relevant too. If it runs fast, then that's cheaper.